Now we'll discuss helium-neon laser. This is gas laser. Okay, this is helium-neon laser, and just a second. So helium-neon laser. Here mainly helium and neon will take. This is a gas. Okay, these are gas, and will take as a we'll work this laser in the gas form. Okay, yesterday we have discussed like it is in uh, solid state. Crystal means solid state, right? Here gas means this is the thing. Okay, this one is discovered by in 1960 or 70, around 1960 to 70. So Bennett and Harriet. Okay, this first these two people are operated this laser, helium neon laser. So here we will get the this is four level laser, four level laser system, and here we will see the 632 nanometer light, that is also red. Okay, so and here we will use the electrical discharge. Okay, electrical pumping, or you can say electrical pumping. These are the key point. Okay, it is four level system, and it will output of the laser is 632 nanometer, and it will achieve the population immersion by electrical pumping. Okay, and this laser is continuous laser. Okay, continuous laser, these are the key points. Okay, so now we'll see construction, and how it will work, how the laser transitions takes place, we will discuss. Okay, so in the construction, if you see construction, here we will take a gas discharge tube. Okay, here discharge tube. You can take like a tube light. Okay, in our home also, how the tube light will work? Anybody, please tell me. Please answer this one. How tube light will work in our homes? No? Do you know how tube light will work?
based on electrical components.
Yeah, electrical, that is also electrical discharge. In a tube light, what we'll do, we'll take some gases, we'll ionize that gas. Okay, once we ionize that gas, there is a atoms or ions will go to excited state and ground state, and they emit the light. Okay, so how we are getting white light means, on the inside of the tube will coat pass-par coating. There is a pass-par coating that will convert a IR light into visible light. That's why we'll see only white light. It's a mixed light. Okay. So that is why here also same thing. Electrically discharged tube will take. Here we will take the helium neon gas mixture. Okay. This gas mixture will take 10 is to 1 ratio. 10 is to 1 ratio will take, and you will give the some power supply to discharge or ionize these gases. Okay, you will give some discharge, and here you will see what you will see. Here you will take the again same thing. This is resonator is everywhere. Any laser you should use the resonator, otherwise will not get the amplified light. Okay, this is resonator. This is 100% reflected mirror, and this is partially reflected mirror. Okay, partially reflected mirror. Partially reflected means half of the light will, some portion of the light will transmit, some portion will reflect. That is mean by partially 100% reflected means it will not transmit any of light, just like a mirror in our home. Okay, it will completely reflect. That's why only you can see your face. Otherwise, we cannot see. Okay, in transparent windows we cannot see. In transparent glasses we cannot see our face, right? So same thing here also. So this is the, here one more thing is there. Here we will add the one more, that is booster windows. These are booster windows. I will explain why this booster windows. Here these two are the booster windows. The booster window. Okay. Here also this one also booster window, I am writing just B. So what this booster window will do, suppose if light is suppose plain light is, suppose here partially reflected mirror is there, suppose you have a slit like this. Okay, you have a slit like this, means a vertical slit. So suppose light is only this vertical components only, it will allow. Okay, suppose there is a perpendicular components, this will block. Okay, this will block the perpendicular component. So these booster windows will convert perpendicular components into parallel components, or plane polarized light, or perpendicular polarized light converts into plain polarized light by using booster windows. That is the job of booster windows. Okay, this is the simple construction you can see here. Booster windows, and we'll take the power supply here. This is the power supply. Okay, this is the power supply. I'm writing just PS. Power supply, booster windows, this resonator or optical cavity. Here gas mixture we are taking 10:1 ratio. Okay, 10:1 ratio. So why here active medium is neon atoms. Okay, not helium atom. Neon atoms are the active medium. Active medium means the medium in which we will get the population inversion and lasing action. Okay, so why we are taking here helium atom means these are lighter atoms. Okay, lighter molecules are lighter atom. Suppose this atomic number is 2. Neon, what is the atomic number?
It's 10.
10, right? Okay. So if you compare the weights of these two atoms, helium is lighter atoms, neon is heavier atom. So suppose here, see, suppose here 5 kg one rock is there, stone, or here 10 kg stone is there, or you can take 2 kg, 10 kg. Okay, here you can easily lift this 2 kg, but here it is required more energy. If you give same power to these two stones or any weight, you can easily lift this 2 kg weight, but it is very difficult to lift the 2 kg weight. That's why here for lifting 10 kg weight, you need more power, you need more energy. That's why what we are doing. So suppose if in the previous solid state laser also input power is very high. So here to reduce that input power, what we are doing, we are taking helium atoms, and first we are giving some lesser energy, lesser input power. We are exciting the helium atoms. Okay, these excited atoms, they are making collision with neon atoms. Okay, once they collision, they make collision helium atoms with neon atoms. Okay, star means excited atoms. Okay, excited helium ion atoms, they will make collision with ground state neon atoms. Okay, once they make collision, they exchange the energy, they exchange the energy to neon atoms. So we are giving initially some lesser energy we are giving to helium and neon. On top of that, helium also giving some extra energy, so that this helium neon atoms will excite to higher energy levels. That is the purpose of we are taking here lighter atoms. Okay, lighter helium atoms. Okay, it is very very simple. First we will take the gas mixture 10:1 ratio, and we'll connect this power supply to this discharge tube. This is gas discharge tube. Okay, discharge tube, you can write here discharge to. Once we give power supply, these ions, these atoms will get energy, they will go to the excited state. Helium atom, so suppose if you give lesser energy also, helium atoms are very lighter, they will easily excite. So these excited helium atoms will interact ground state neon atoms. Okay, excited helium atoms will interact ground state neon atoms, and during this collision or during this interaction, helium atoms exchange energy to neon atoms, or helium atoms gives energy to neon atoms. So once the neon atoms collect energy, receive energy, they will also excite to higher energy levels. Okay, once they excite higher energy levels, there is a spontaneous emission and stimulation emission process takes place. Okay, and we'll get the population inversion. First spontaneous emission takes place. After that, atoms will accumulate in metastable states, and this spontaneous emission, during spontaneous emission, photons will emit. These photons will trigger the stimulated emission process. So like that we will get the stimulated photon also. These photons will use the amplifier resonator, and suppose if it is not multiple times, here reflect 2 and 4 at the back, at the 100% reflector mirror, then this all will come into same phase. Okay, all they come into, all photons will come into same phase, and this will emit from the partially reflected mirror. Okay, partially reflected mirror. So this brewster angle, suppose one is plane polarized light, another is perpendicular polarized light. So this booster windows make them all should be in plane polarized light. Okay, that the use of the booster windows. Okay, Now we'll see the energy level transactions. Okay, suppose polarized means light generally propagate in three directions. Okay, x y z direction. Okay, x y z direction. Polarized means only one type of components will allow. Suppose x component or y component. Okay, that is mean polarized light. Okay, now we'll see energy level transition. How will energy means this lasing action takes place in a atom. We will see. So here helium is there. First you take helium. Okay, helium energy levels, and here you take neon energy levels. Okay, neon energy levels. Because why we are drawing two energy levels means two atoms are there. We have to consider. Actually yesterday also I discussed why we are mixing different elements means to create a different metastable state. Okay, any doubt? Are you having any doubt?
No, sir.
If you have doubt you can ask me anytime during in class. You can ask anytime, you can stop me anytime. Okay, no problem, I don't mind.
Sir, do here also we will use the same element to reach metastable state?
Same. Sorry, I could.
Do we use same element to reach metastable state in this also?
Same elements means here different atoms are there, no? Energy levels also different. Here suppose if you take any atom, every atom having different energy levels. Okay, depends on that energy levels we'll get the laser transitions. Okay, is that, are you asking or any?
Sir, I was asking that which ion will use over here to reach metastable state?
Some disturbance is coming your side, I could not hear your question here. Can you repeat it again?
Sir, I was saying that which ion we will use over here to reach metastable state?
Which ions?
Yes, sir.
Here we will only excite the atoms. Ions also will excite, but neon ions, once the neon will lose the electron, that will ionize it, right? This will also excite. Okay, atoms will excite and ions will excite. Okay. So here we will see the. Is it okay?
Yes,
Is it
sir.
clear? Okay. So okay. Here we will draw the energy level diagrams. Okay. Here if you draw this one here. First we will take the this one. Just a second. Right again. So this is a little bit complicated compared to this three level system. Here more levels are involved. Okay, this is helium and this is neon. Okay. So here I am drawing energy scale. Okay, just energy scale. Okay, this is energy in terms of electron volts. Okay, electron volts. Electron volts. So here write 16, 18, 20, 22. These are electron volts only. Okay. This time writing electron volts. Okay. So here the energy levels, helium energy levels are like 19, 21. Here 19, just like 19 and 21. These two are energy levels. This is ground state energy E1. Here also you can mention it ground state energy E1. Okay. This is just you take E2 and E2 dash. E2 and E2 dash. And neon also there is a energy levels closely matched with helium atoms. Okay. Here you can draw two more energy levels for neon. Okay. Just take neon energy level, one more here, another here, and here you can draw energy levels for neon. One is at 16 electron volts, near about 16 electron volts. Another is about 18 electron volts, and another about 20 electron volts. Okay, these are the. Let's take this one E1 dash. This you can any you can take it as your wish. Okay, There is no rules for this selecting these levels. Okay, E3 and this E3 dash. Okay, this is E4 and E4 dash. Okay, E1, E1, sorry, E1 dash. So ground state, first exited, second, third, and fourth and fifth like that. Okay. Or you can take 1, 2, 3, 4 also, it's not a problem. Here you can take E1, E2, E3. Here also you can take E1, E2, E3, E4, E5, E6. Like that also you can take. There is no problem at all. But you see the energy range, okay, where you are drawing, and from where to where these transitions are taking place. That is most important. Okay. So we have drawn these energy levels. Now we will see how the atoms will excite. Okay. We are giving, suppose initially we are giving some using power, by using power supply we are giving some input power to gas mixture. Okay, helium neon gas mixture. Suppose if you give small energy also, this helium atoms will excite to these higher energy levels. Okay, some of the atoms will go to the this level, and at the same time if they have higher energy they will go to the excited state. Okay, so here E2 dash also metastable state, and E4 and E4 dash also metastable states. Okay, so here I am writing metastable state. So here we are not writing higher energy levels. Okay, higher energy levels. So why? Because already many levels are there. It is making
Making
complicated.
complicated.
That's why we are not writing. So here, which one is having higher lifetime? E2 or E2 dash?
E2 is having, sir.
Yeah, E2 is having higher lifetime, that is 10 power minus 4 second, and this is E2 dash is 10 power minus 6 second. Okay, these are the energy levels. Same levels will match with neon atoms also. This is also metastable, lifetime is 10 power 4 second and 10 power minus 6 second. Okay, and E3 dash is slightly lesser than the E4 dash, and E3 these are sorry, slightly higher. Okay, so this one also E3 and E1 dash also slightly higher compared to E4 dash. Okay, so here see how we are writing this energy levels. This lifetime. See here, you can no need to by heart this one. E is equal to what we know h nu, right? Time means you can write this is 1 by tau. Nu is equal proportional inverse proportional to time, right? Isn't it? Frequency.
Yes, sir.
Yeah, we can write E is proportional to nu, yet proportional to nu frequency, that is. Now E is inversely proportional to time period. That's why when energy is less, lifetime is higher. So if you take ground state, energy is zero, lifetime is infinity. So if you take energy is increasing means lifetime will decrease. This is the relationship between energy and lifetime. That's why we are saying ground state is higher lifetime, infinity lifetime. Okay. So here also, if E2 is the about 19 electron volts and E2 dash is the about 21 electron volts. So that's why this lower energy level is always having higher lifetime. Okay, you remember this one. Okay. Now we are giving some energy, this helium atoms making transition to this metastable state. So here also one more point you can see here. These atoms will go to the higher energy levels also, but we are not drawing these states. Why? Because only whatever useful for the laser transition only we are drawing, and these are many levels are involved here, so it will make more confusion. That's why I am not drawing. Okay, once atoms, helium atoms are going to the excited state, they will make spontaneous emission. Okay, more light will emit. This will again activate the reactions. Okay, because this will also, this emitted photons also gives some energy to the helium neon atoms. Okay, so once they excite this state, what this will do, helium atoms again, this excited helium atom, suppose helium, excited helium, I am writing star. Helium atoms will make collision with ground state neon atoms. Okay. So once they interact, once they make collision, helium atoms, excited helium atoms change some, give some energy to the neon atoms. Okay, once they get the neon atoms energy, they will also excite to the these two levels. Okay, E4 and E4 dash. Okay, E4 and E4 dash. So how these neon atoms are exciting here? How we are getting neon atoms in this stage? By collision. Okay, by collision only, by interaction only, we are getting the neon atoms to excited levels. First, what we are doing, we are giving same energy to helium and neon gas mixture, but helium atoms easily exciting with small energy, but neon atoms required more energy to excite higher energy levels. That's why we are utilizing the excited helium atoms to make the transition to higher energy levels of neon atoms. To send the neon atoms to higher energy levels, we are utilizing excited helium atoms. Okay, is it clear this point?
Yes, sir, clear.
Okay, first what we are doing, first we are sending the helium atoms. Okay, so now helium atoms are having higher energy. These excited atoms along with input power is there. Input power we are giving same helium and neon, we are giving same input power. Okay, suppose 5 joule we are giving to helium and neon. This 5 joule is not sufficient to lift these neon atoms, or this 5 joule energy is not sufficient to send these neon atoms to excited state. That's why these helium atoms are interacting with neon atoms. Okay, are making collision with neon atoms, and they giving some energy. They are giving some energy. So addition to this 5 joule, some extra energy is getting, then these neon atoms going to the excited state. Okay, this is just example 5 joules, it's not exact value, just for understand I take a some value. Okay, so first we are giving energy and we are sending the helium atoms to excited states, and this excited state helium atoms making collision with ground state neon atoms. Once they make collision, they exchanging the energy. Okay, they exchange the energy, and neon atoms get sufficient energy, they will also move to the higher energy levels. Okay, now the lifetime also here very high, so now they have to make transition. So why we are not making another level? So already there is a spontaneous emission is there. Okay, I am not drawing here that level. So if you draw here excited state, these atoms will make here also. Okay, then they will come to the metastable state. Here they will emit the spontaneous photons. Okay, spontaneous photons. So we are not drawing that step. Okay, you find out here, you remember here. So atoms are accumulating in the metastable state. So some of the photons should trigger these atoms. So who will trigger that one? Whatever emitted photons in the spontaneous emission. Okay, whatever photons emitted in the spontaneous photon trigger these atoms, these neon atoms to the lower energy levels. Okay, that are spontaneous transitions we haven't drawn here. Okay, to remember here. Okay, now these atoms, excited state atoms, there is a two possibilities. They can come here and they can come here. Okay, right? Here there is a two energy levels. They can come the atoms. They can come here also. They can come here also. From here also, this E4 dash here also, the atoms can come here to here. Okay, there is a probability. Okay, here how many transitions are taking place? Total three transitions. This is first and this is second and this is third. Three transitions are taking place. First one, E4 dash to E3 dash. You can write here E4 dash to E3 dash, first transition. Next one, E4 dash to E3, and final one, E3 to E3, E4 to E3, E4 to E3. These three transitions are taking place in helium-neon gas system. Okay, once they make, this is the 3.36 micrometer, and this is the most famous or more dominant transition, 632 nanometer, and this transition is 1. I can write 1.15 micrometer. Okay, So depends on our requirement, we can use the laser. Mostly helium neon laser means we will use the this transition. Okay, we will use the this energy. We will use the this power to many applications. Okay, so first we are, what is the process here going on means, first we will excite the helium atoms. Okay, we are giving same power to helium and neon, but helium easily exciting. Okay, so neon need our neon atoms required more energy. So we are initially giving some energy, but that is not sufficient. So this neon atoms taking energy from excited helium atoms. Okay, helium atoms will make collisions with neon atoms in the discharge tube, or helium atoms make interactions with neon atoms in the discharge tube. They exchange the energy. Okay, once neon atoms get the sufficient energy, they will make transition to this metastable state. This is also metastable state. This is also metastable state. Okay, here atoms, and they will go to the higher energy level also. After that, they immediately come to the this metastable state also. Depends on energy. If you give more energy, they will go further higher energy level also. But we are not drawing that one. Okay. So once they go higher energy levels, they make lifetime. If it is lifetime is very less, they immediately come to the metastable state, and in the metastable state, atoms will accumulate. Atoms will stay for some time. Okay, this during this time, atoms are staying in metastable state. So whatever photons emitted in the spontaneous emission process, trigger the stimulated emission process. Okay, once triggering means there are three different transitions takes place during this stimulated emission process between these neon energy levels. First one, if you say E4 dash to E3 dash, this is atoms. There is a chance of these atoms can come to the E3 level, and there is a chance of these atoms can come to the E3, and also another metastable state E4. From E4 also there is a chance of come to the E3 level. Okay, once they make stimulated emission E4 dash to E3 dash, that will emit the 3.36 micrometer wavelength photons. Okay, micrometer wavelength photon. If suppose they make transition from E4 dash to E3 level, they will emit the 630 nanometer light, 630 nanometer light, or 630 nanometer photons. And third one, if atoms will make transition from E4 to E3 level, they will emit the 1.15 micrometer photons. Okay, now atoms are accumulated in the E3 and E3 dash. After that, they will come to the E1 dash by a spontaneous emission, by de-excitation, or these atoms will make collision with discharge tube, or they will after transition they will come to the this E1 dash by spontaneous emission process. Okay, now atoms are E1 dash. From there, they will come to the ground state. This is, they will de-excitation. Okay, here they will take de-excitation. Here atoms will in E1 dash, what they will do, they will make the collision with walls of the discharge tube. Okay, once from after making after emitting the photons or light from E3 level to E1 dash, they will come as a spontaneous emission. Okay, here also photons will emit. This photon again interact with neon atoms. They will send to the excited state. Okay, again after this E1 dash, these atoms here they will make collision with discharge tube wall. Okay, so after that they will come to the ground state, again go to the excited state. Okay, because here we have a gas tube, right? Gas tube means this helium and neon atoms, they can freely move here and there. They can move throughout the discharge tube. They can freely move. Okay, there is no restriction to this helium neon atom, but the helium atoms move very freely compared to neon atoms, because these are lighter, right? They can easily move freely. Okay, so after they come ground state, again they will go to the excited state, again they will make the transition. Okay, here the lasing action, here we will get the population inversion continuously. That's why this laser is continuous laser. Okay, This laser is continuous laser because we can achieve population inversion continuously. There is no stopping for the lasing action. Okay, this is the working of the construction and working of the laser and how the laser transition takes place. Okay, so I am explaining again, clearly see it one. First we will take a helium neon gas in a discharge tube. Okay, we will give some power to the discharge tube, and we are giving power to the helium and gas mixture. In this gas mixture helium, we are taking these helium atoms are just like a catalyst or activators, or you can say. Okay, if you give some small energy also, helium atoms can excite, but neon atoms cannot excite because these are heavier atoms. Okay, once we excite helium atoms, they will interact with neon atoms, ground state neon atoms, and they will exchange energy. So when neon atoms reach get the sufficient energy, they will also excite to the higher energy levels. Here E2 and E2 dash and E4 and E4 dash are same equal energy levels. It's not exactly equal but almost equal. So these are metastable states. Lifetime is 10 power minus 4 second and 10 power minus 6 second. Okay, once they interact with neon atoms also excite to the metastable state, and atoms will accumulate in the metastable state because of the higher lifetime. So here someone should be trigger these atoms to make a stimulated emission. So here we will trigger means whatever photons emitted in the spontaneous emission, they will stimulate these atoms in the excited state. Okay, so after that, after triggering, these atoms make transition to lower energy levels. There are three possible transitions in the helium-neon laser. First one, E4 dash to E3 dash, that will emit 3.36 micrometer wavelength photons. And second one, this is famous and most dominant transitions in the helium-neon laser. Okay, most dominant transition. Okay, E4 dash to E3 dash. Okay, that is 21 electron volts to about 18 electron volts. Okay, that is 632 nanometers. Second, last one, that is third one, E4 to E3 dash. Okay, after that it will emit 1.15 micrometer light. Okay, after the stimulated emission, atoms will come to the E1 dash level or E1 dash state by spontaneous emission. Okay, so now atoms in the E1 state, they will make collision with surrounding walls, okay, walls of the discharge tube, and they will come to the ground state. Again they will go to the excited state. This will continue. Okay, there is no discontinuity in the population inversion and lasing action. That's why we'll get the lasing continuous laser beam in this seal. So here 632 is emitting, right? So you see the transition, which level to which level is taking place, which level to which level, energy range you tell me is 21 to 18, right? Isn't it? 632, 632 632 nanometer light is emitting between E4 dash to E3 dash, right? Isn't it? Can you see it? E4 dash to E3 dash, right? That means
Yes,
here
sir.
lambda is equal 1240 by E4 dash to E, E3 dash, right? E3 dash. That means 1240 by 21 minus here 19 or 18 electron volts. Electron volts. How much it will? About 3 electron volts, right? 3 are about 3 3 electron volts. About 3 electron volts. That means can write exactly 18 or this is about 21 to about 19. It will about 19 like that. Okay, 19 means about 19 this level, say E3 dash level. If you see this one is about 19. Okay, if you take about 19, you will get the 1240 by 2 electron volts. So it will around 600, 620 nanometer. Okay, 620 nanometer. So 620 nanometer means red. Okay, just you can estimate the wavelength by different transitions. Okay, different transitions. Okay, what are the applications? What are the applications here? What are the advantages? First, it is a continuous laser, and here we will get the more chromatic and more directional. In this laser, it is a continuous. Advantages of this laser is continuous, first one, and more directional and more chromatic. Directional and more chromatic. Chromatic means one color. Okay, and it is less expensive. Okay, these are the few advantages. Less expensive. That's why. So these are the few advantages. It is a we can produce the continuous laser, and we can this laser is more directional, more monochromatic, and less expensive. Okay, these are the few advantages. Suppose here you are getting the continuous lasers, right? You can use the switch here. You can start and you can off for some time, and you can start like that also. You can use this, can you be used as continuous and discontinuous, but mostly used as continuous laser. Okay, next, we have applications, several applications. Suppose for scanning purpose and QR code scanning purpose. If you go shopping, they will scan, right, your card or something like that. You can use that one, and also you can use the speed control or some alignment. Some suppose something you want to detect. This also you can use. Okay, these things are applications, and drawbacks are short lifetime and low output power, and it required more time to initialize. Okay, more power to initialize. Okay, here slightly input power also higher compared to semiconductor lasers. Okay, tomorrow we'll discuss semiconductor lasers. Okay, now I'm stopping. Any doubts here? Anybody having doubt here? If you have doubts, you can message me, or tomorrow also you can tell me. We'll discuss. Okay.